They're pretty well known.
All right. Hello, everyone. Thanks for coming to today's Slido talk. So today we have Peter Frazier, who was a professor at Cornell, working on operations research, machine learning, game theory, AI for science, and a variety of different topics. He has a lot of influential work on Bayesian optimization. I recommend many of his papers. I've read them. I've really enjoyed them. He has also applied many of his works on real-world use cases. He led the COVID-19 response at Cornell. He also has deployed some of his methods for pricing at Uber. And now he has taking all of these expertise to his startup called Satellite Labs. His work has been recognized with many awards. I won't list all of them here, but they include Best Paper Awards at ACADC, at Informed, and also some of the faculty from NSF and so today he'll be telling us about Bayesian preference learning. So, take it away.
Thank you, Kirti. It's great to be able to be here. I've had a lot of great conversations with people, and it's wonderful how many interesting people there are in a variety of different departments. I'm going to present you work which is joint with quite a few people, covering a collection of papers over the years working in Bayesian preference learning, but I especially want to acknowledge Raul Estagino, my former PhD student, Jerry Lin, and Eitan Bakshi at Meta. I have a background in Bayesian optimization, like Kirti, and I'd like to tell you about this area because a lot of what I'm going to talk about comes from this background. So Bayesian optimization is a methodology for optimizing time-consuming to evaluate non-convex objective functions when you lack the ability to evaluate derivative information. And it also tends to work well when you have a prior knowledge about the problem that you can encode with a Bayesian prior probability. So the way that these methods work is they build a surrogate for the objective function. So here I'm showing you a one-dimensional optimization problem with a decision variable x and some objective function f of x that I'm trying to maximize. And I'm showing you the fit from a method that's called Gaussian process regression that provides an estimate for the objective function. So the objective function is shown here in green. I've evaluated it at these green points, and the estimate is shown with this solid blue line. And then I have uncertainty about the objective function value shown with this shaded region in blue. Bayesian optimization uses this probabilistic surrogate to quantify the value of a new objective function evaluation as a function of when you perform the evaluation. I'm showing you and this is called an acquisition function, and I'm showing you the output of one common acquisition function called expected improvement for this particular problem. And you see that it tends to be large at places where my estimate for the objective function value is large, and here. And it also tends to be large at locations where I have a large amount of uncertainty about the objective function value. So that's why the acquisition function is maximized, like at this point here where you have both of those properties. In Bayesian optimization, we would then perform an evaluation of the objective function at this point that maximizes the acquisition function. We would update our posterior distribution, recompute our acquisition function, optimize it, find the new place to evaluate, and repeat. And if we've done a good job of setting up our surrogate model, and if we have a little bit of luck, then after a small amount of evaluations, then you will find a solution, an approximate solution, which is close in value to a global optimum, if things go well. These methods have been used by tech companies for about maybe 10 years to optimize hyperparameters in time-consuming to train and evaluate machine learning models, deep learning models. So, for example, these systems or these algorithms are used to choose the learning rate, other hyperparameters inside of deep neural networks. So the way that we think about this is that there's a collection of hyperparameters for a machine learning model. I can train and then test my machine learning model that's created using these hyperparameters and get some performance metric. And what I want to do is I want to optimize this by varying this. The other place where these methods are widely used in the tech sector is for optimizing products. So, many of you have Instagram on your phone, and within Instagram, there's a bunch of different algorithms that choose what to show you at different points in time. Those algorithms have parameters, and those parameters are tuned by a group at Meta, led by my collaborator Eitan, that uses Bayesian optimization algorithms to figure out which choices for those algorithm hyperparameters should be evaluated. And the way that they're evaluated is people in the world are randomized into two groups: a control group that gets regular old Instagram, and a treatment group that gets the new version of Instagram with these different hyperparameters. And then metrics are examined, like how much time do you spend on Instagram to produce a measure of quality, and then Bayesian optimization is then used to tune X. Okay, this is widely used and it's pretty standard. And there's great software packages and lots of good algorithms and theory for doing and understanding this area. A challenge, though, in many problems is that we don't know what the objective function is. For example, suppose that I have hyperparameters in some generative AI pipeline, maybe that converts a text string into an image, and I'd like to tune these hyperparameters because that's what I'm used to doing. And usually we need to tune these systems in order to get them to work well. Great, I can take some prompts and generate some images using my AI pipeline. But then the problem is when I go to evaluate the quality of these images, it's not really clear how to do it, right? And that's a prerequisite for being able to optimize something is to be able to evaluate the objective function. Another setting where we don't know the objective function is Uber, where I worked for a number of years. We would, do what they do at Meta, where I would have an algorithm that has some parameters that I want to optimize. And I would run an A/B experiment where maybe I would randomize riders into treatment and control, or drivers, or maybe I would randomize time periods in a city into treatment and control. But somehow I would try out this new set of parameters, and I would produce not like one number that tells me how good those parameters are, but I would actually get a bunch of numbers, a panel of metrics. And, it's good when revenue goes up, but it's bad when profit goes down. And so how do I make the trade-off between revenue and profit? It's not clear. So what do we do in this situation? So many people, myself included, will attempt to specify a utility function. And let's take this case of a panel of metrics at Uber, right? So I might choose to create a linear utility function over all of these metrics, right? So I would talk to executives at the company and decide how much extra revenue do I need to be willing to, how much extra revenue do I need to get in order to make up for a loss of $1 in profit? And I would use that to choose these coefficients, right? And then once I have that, now I have an objective function, and I can use single objective Bayesian optimization to maximize the utility of the panel of metrics y of x. So y of x here is a vector valued function of my decision vector x. The problem is, if you sit down, vice president of product at Uber and you say, what's the weight on revenue versus profit? It's hard. You're not going to get a straight answer, right? They're not going to commit to a number. Another idea is multi-objective optimization. So I would try to estimate the Pareto frontier. So the points on the Pareto frontier. So each point here is a vector y of x for an x that's feasible. And a point on the Pareto frontier is a point such that if I want to improve revenue, I need to decrease profit. Okay, so I would use what's called the multi-objective Bayesian optimization, which chooses x's to evaluate in order to find all these points on the Pareto frontier. Then in my meeting with the vice president of the product, I would sit down with him and I would say, hey, Sandeep, here's the trade-off curve. Why don't you choose a point on this curve? That works pretty well when you're only working with profit and revenue. But if you add a third metric, which is like how happy are drivers, all of a sudden the dimensionality of the search space is larger, the number of points on the Pareto frontier is larger, and it takes a lot more experiments to estimate everything. And if I want to add a fourth metric, how happy are riders? Or how happy are riders in Cleveland? How happy are riders in New York City? All of a sudden, the dimensionality of the Pareto frontier is very large, and we need too many experiments in order to be able to estimate. So in this talk and in this line of work, we're proposing an alternate solution. And it's motivated by what I did in an applied sense at Uber. So at Uber, when I was working with a decision maker, like this is Margaret. Margaret was the applied science manager on the team that I worked on for a number of years. She made the decisions about like what product to launch, but I knew how she thought, or I had a good sense for how she thought, right? So if you showed me a panel of metrics, a lot of the time, two different panels of metrics, a lot of the time I'd be like, Margaret's going to pick that one, right? Why is that? It's because Margaret, I think, has a utility function, an objective.
Panel of metrics just means a point on our end now. That just means like
Point in our end.
Okay, great.
So a panel. This is a point in our end. So each component of like a vector in our end is associated with a business metric. Like ETA is how long the car takes to come pick you up. This is how long you wait. I should probably explain this. This is how long you wait on the app as a rider before you get told the driver is going to come and pick you up. So this is the first component, second component. So this is, there's an associated point in R 1, 2, 3, 4, 5, whatever, 6. So panel of metrics is a point in R6. Thank you. Other questions? Please stop me when you have questions. Right. So if you give me two panels of metrics, a lot of the time I would know which one Margaret would pick. She has a utility function over these panels of metrics. It's just that it's hard to get her to write down what that is as a mathematical equation. Right? It's not that she lacks mathematical expertise or that she's dumb or something. It's just that we as humans have trouble converting the things that we want into equations. So the solution that we've developed is a two-step solution. So we asked the decision maker, Margaret, indicated by DM, we asked her questions in order to learn her utility function over panels of metrics or, pictures of chairs that look like avocados. Then we're going to use what we've learned, which will be kind of quantified via a Bayesian posterior distribution over utility functions to choose which A/B experiments to run, or which generative AI model hyperparameters at which to train in order to essentially elucidate the part of the Pareto frontier that's most likely to be preferred by our decision maker.
Yeah. You may have
her own preferences to rank between a pair of items.
Yeah.
She does not necessarily have a value or utility function, like rocks your paper kind of scenario where she prefers this over this, so there's circular things going.
You're asking like, you're saying like people are inconsistent sometimes. Like I prefer rock over, I prefer paper over.
Consistent, but I mean it's consistent over the three items.
Yeah.
Right. But it doesn't necessarily give us any utility function. So being able to choose one over the other in every case doesn't necessarily mean you have a utility function that exists.
Yeah. Yeah. So the question is that like just because I'm able to compare things, like comparison is just about saying that the utility of the thing I prefer is strictly larger than the utility of the other thing, and so it's a ranking, and it's not. There's no numbers associated with it. We're going to make an assumption in this work, which is also common in other work in preference learning, where we're going to suppose that people give us noisy answers. And if I give you two things that you're kind of like, the difference in utility is small, then your answers are noisy, and the level of noise in your response is larger when the difference in utility is small. But if I gave you, if I was like, would you prefer to, this afternoon, like have a cup of coffee or get hit by a bus? Then every time you're going to be like, I prefer the cup of coffee. But if I'm like, would you prefer a cup of coffee or a cup of tea? Maybe. Yeah. So that's the kind of mathematical assumption that we're going to make. And then because of that mathematical assumption, along with kind of a parametric link function that we're going to use, it's going to end up implying quantitative values for utility. Now, you could ask, like, is that real, or is that just a modeling consequence? And I think that would be a legitimate criticism, and there's probably same work to be done, kind of that. There was another question?
I was just going to ask, okay, let's grant your hypothesis, but even so, any real company has multiple decision makers. So I'm worried that puts you right back to the situation of now there's a new Pareto frontier with your 5 different decision makers. Yeah. Variables.
I have lived this. Yeah, Margaret doesn't always agree with something. That is a limitation. That is a limitation of the papers that I'm presenting. And it's an really interesting opportunity for future work, where you could take the modeling ideas that I'm presenting here, and you could say, like, hey, there's Margaret, and then there's Sandeep. You can even model the decision-making process. And you could do what I have done from an applied perspective, just trying to work things out as a human, which is to then say, hey, if I showed Margaret and Sandeep this collection of options, this is what's going to happen in the meeting, and then here's what's going to happen when it escalates to the CEO. So you could in principle build a model of all of that, and I think it's very interesting to do that. I have not done that, yeah, it's a good question. Yeah.
The question I had was about the real dimensionality of the panel. Like, I guess decision makers won't look at 20 variables, right? Eventually, maybe your utility will be like 2, 3, or do you think?
It depends on what the change is. So, I would say that there's two kinds of. It depends on what the change is. People do really care like if you do a product change where you move all of these things, and kind of anything above maybe 0.2% is meaningful. If you move any one of these metrics by 0.2%, you better tell people, because they're going to care. Now, so you kind of have like 5 metrics. You are often in situations where I'm not changing anything on the driver's side, and so I'm not really changing driver earnings by very much, or I'm only changing something on the driver's side, and I don't know, sometimes you're only changing 2 or 3. In that case, yeah, you're kind of a Pareto frontier. I would say that most of the time, a product team is looking at between maybe 4 or 5 metrics. There are situations where people are looking at maybe 10 metrics, 20 metrics. Yeah, would be kind of weird.
I guess probably there's a relationship between how noisy the decision maker will be and then dimensionality. I mean, meaning how, probably there will be degradation of their ability to decide. But
it's true that the cognitive load associated with looking at like 10 metrics is higher than looking at 5 metrics. But, also keep in mind, like, if it's your job and like a change could be sort of making the right choice could be worth $20 million in terms of impact on the world. So yeah, people usually, product managers at Uber and are reasonably are very thoughtful in terms of like figuring out which thing they would want to launch. Yeah. Okay. So this is the strategy we'd like to pursue, and I want to tell you about the algorithms, and then I want to tell you about some ways that this has been launched at Meta, actually, rather than at Uber, because Meta is a bit more open about joint research. So the solution, and this is like basically just a diagram explaining what I articulated before. We're going to have an iterative process where I'm going to select pairs of solutions to present to a decision maker, and then I'm going to ask that decision maker which one they prefer. I'm going to use this to learn to use a posterior distribution over utility functions. Then I'm going to use that to select one or more x's at which to run an A/B test to observe some outcome, y of x, and then I might iterate this several times. And then at the end, the decision maker will select the x amongst those that we've evaluated that has the largest utility to them. And we're going to think about the decision maker as when push comes to shove, maybe they can't tell me what equation describes the utility function, but they are able to select among the x's they're able to choose which one is best for them. And I'm going to have this diagram a lot. So we think of the way that user utility for a decision is being produced as the decision goes through some forward model. So in the case of Meta or Uber, it's like an A/B test where I'm deploying some system in the real world and I'm seeing how well it works. That produces an outcome vector, which is a panel of metrics. And then that goes through this user utility function, which produces the utility.
Can I ask it?
Yeah.
Right, you're going to sort of posterior distribution over that mapping of Y's to the utility.
Yeah.
You can just propagate that uncertainty all the way through, or you're just going to use like the posterior mean.
We're gonna do our best to propagate the uncertainty about you like through the whole pipeline. There's probably when I do that, I'll show you maybe some shortcomings of what we're doing, and there's opportunities to perhaps improve on the algorithm approach that we're doing. But yeah, in principle, we aspire to that, subject to computational. I come to this from the perspective of Bayesian optimization, but I want to argue that this is an instance of a larger problem class that like people who do optimization might be interested in. So we have some kind of we have an unknown user utility function because the user can't tell me what they want, and I have a way to interact with the user to understand that utility function. So through the bulk of the talk, I'm going to focus on presenting pairs of items and asking people which one they prefer. This is well supported in the literature around preference learning as a robust kind of way of doing human subjects research. But now in the world of LLMs, it's becoming easy to do things like have some algorithm generate a question, right? So you might present a pair and then ask, why do the user selects y over y prime, and you can ask, why do you prefer that? And the user might reply back to say something like, "Hey, we're really trying to prioritize driver earnings in Q3 2025 because we think it's really important." Or we're trying to hit, some financial target, and if we can increase revenue, that will help me hit my financial target for the quarter, right? So you get this text, and we can start to think about incorporating that richer kind of feedback into posterior distributions over utility functions. And I won't have time to go into detail, but I'll hint at some work, some ongoing work that's doing that. So you can generalize how we do user interaction. You can also generalize this orange box, right? So I'm thinking about like a zeroth order oracle where you pass in an X and you get a Y of X. But we're also very interested in applications where you have a kind of a large scale optimization problem, and you can pass in a utility function and you can get an X star that maximizes that utility function, right? And so the broader question is, how should I use a limited budget for user interaction and forward model interaction to find solutions that maximize user utility? And I feel that a broader set of methods for this larger class of problems would really increase the impact of optimization methods, and really accelerate the use of optimization in the real world. So how applied optimization, coming from an OR department, here's my view of how applied optimization works today, right? So some company or some large entity has a problem where they think optimization could help. They hire someone who has a PhD, or maybe a team of people who have PhDs, who are OR experts or optimization experts, to create a solution, right? The OR expert works with them for weeks or months. They write some software, they iteratively understand what the decision maker wants, and then they launch something in the real world. And it takes, 6 to 18 months, and it costs at least like $300,000. That means that people who have optimization problems where they can't afford waiting 6 months and they can't afford $300,000, they just kind of make the decision, however, based on intuition, or they put it into ChatGPT. But if you could shorten this cycle and you could have something that's a lot more efficient, be able to figure out, to be able to do this part of the work, then just greatly expand the number of people who can use optimization. And this is motivated by just a couple different projects. First, you mentioned an asymptomatic screening program that we set up at Cornell, where we use a lot of optimization. We did this with university president and provost and people who run the lab in order to be able to reopen the university with low infection counts. I have a project right now with Jeff Linderoth, who is currently at a military exercise in Southern California, where we are building mixed integer programming models to support the U.S. Marines, where they have exactly the problem where they don't know what they want, and then also scheduling final exams at Cornell using mixed integer programming with David Schmidt. Okay. So, all right. So that's the big picture of where I think this kind of broader effort can go. I want to sketch our solution for the more narrow problem at Uber and at Meta, where the forward model is a zeroth order oracle from A/B testing, and where the way I'm interrogating user preferences is through pairwise comparisons. This is related, and I want to acknowledge that this work is related to a number of areas in multi-objective Bayesian optimization that I mentioned: preference learning, active learning, utility elicitation. So just really building on a large body of work here, and then also in what's called preferential Bayesian optimization, where you forget about the forward model and you just imagine that you're trying to choose X in order to directly optimize U of f of X. And then also related to an exploding area of work in kind of inspired by large language models for doing RL with human feedback. Okay, so I'll sketch the solution. So I'm going to use Gaussian process regression. I introduced this at the beginning. It's a Bayesian method for doing inference over functions. And essentially it's linear regression on steroids, where I have what's called a kernel that encodes an assumption about the relationship between the function value at two different points as a function of how far away they are from each other. And it produces as an output, again, an estimate of the function it's trying to model here in this solid blue line, and then confidence regions. So the way that we do inference, and my focus here is on the experimentation. So choosing which questions to ask the decision maker and on which A/B tests to run. So I just kind of very briefly want to mention how we do the inference. So the way that we model, we're going to build Bayesian models for both of these. So the way we model this is just using a vanilla Gaussian process where slightly like vanilla plus. So it's a multi-output Gaussian process. So this is a way of modeling the relationship between a vector and a vector. And one example of a multi-output Gaussian process is you just build a separate Gaussian process on each on the mapping from X to each component of Y events. And then for user utility, we also essentially use a Gaussian process, but there's a twist in that we model the user as, okay, there's a typo here. So we model the user when they choose between Y and Y prime. What they do is we imagine that they compute the utility of Y and Y prime. They take the difference in utilities. There should be the difference in utilities divided by some unknown parameter lambda. And then this gets pushed through the logistic function or some other function that is strictly increasing and starts out at 0 and goes to 1. And then there are computational tricks for being able to approximately compute the Bayesian posterior distribution with a model like this.
That probability, should it be U of Y minus U of Y?
It should, yes.
Okay.
Yes.
So can I ask you, is this an alternative to the preference elicitation that you did before? So is that part just gone where you ask the questions, or is?
No, this is how I take the questions and convert it to a posterior distribution over utility function.
Okay.
Yeah.
So when you have these intermediate metrics like in Uber, I guess learning that intermediate vector y of x would be relatively straightforward. But if you're doing like a pairwise comparison, when you're comparing to like an avocado picture of an avocado like a chair, then how does that work? Do you still use the same model, or do you use something slightly different?
We use them. So for pictures of avocados, so one way to work with pictures of avocados is Y is just like the pixels. Another way to work with pictures of avocados is like there's a low dimensional embedding of the pictures of avocados, and well, not that low dimensional, but there's an embedding of the image into a vector space, and so we take that to be the Y. Yeah, and so that has the advantage of like, you know, two pictures of avocados that are similar to each other are going to tend to be at similar points in the vector space, and so you kind of are leveraging the continuity assumptions inside the Gaussian process to be able to. Yeah.
Do you only ever query the decision makers with panels that are actually produced by the forward model?
We do not. So that is a really interesting question. So, so the method that we develop queries the decision makers with panels that are plausible. That it's like it's plausible, and like what we do is we take a sample from the posterior distribution over like there's some feasible set, So I don't know what this function is, but I have a GP on it. And so I can sample this set. And then the whys that we ask the decision maker about come from this set. So they're plausible. And that's important because if you're going to ask the product manager to have a meeting with you, it needs to have like an air of, it needs to be kind of realistic. Otherwise they won't like pay attention.
And then follow-up question. So wouldn't it make sense to kind of try to derive an acquisition function on that space as well? So that the same ideas that you use in your orange region.
This is exactly what we do. So when we, I'll define an acquisition function for you, which will be over pairs of y, pairs of points y, and then the pair y prime that maximizes the acquisition function. That's the question I'll ask the decision maker. Yeah.
Are you fixing lambda? Otherwise, you're like none of this is that end of.
We don't fix lambda. It's true that it's not identified, but we're Bayesian, so it's okay. We have a prior. You kind of have a prior on the length scale of the GP, so that means that despite the fact that it's not identified, you get a posterior distribution over lambda. You could also fix lambda and then yeah, and then what you would want to do is have a more flexible prior over the scale of the output. Yeah. Okay. So we can do inference given data. How do we decide on the A/B test to run? So I showed you standard Bayesian optimization. Let me tell you just like epsilon more about the acquisition function. So I've evaluated in regular old Bayesian optimization where I know the objective function, I've evaluated the objective function at these points and let f star denote the maximum objective function value that I've observed. Imagine evaluating in a new point x, I would observe f of x. The new best value that I will have will be this thing without the expectation, right? Because it's either the old best thing or the new thing. And I can take the expectation of this. So this quantity is random because I don't know what f of x is before I evaluate it. So I can take its expected value, and the kind of the most widely used acquisition function is just defines the this quantity, which is like the expected value of the best solution that I will have found after measuring at x, minus the previous best value. And this is called the expected improvement. And it's kind of got embedded within it this idea of looking one step ahead. We're going to take the same notion, except we're going to extend it to a setting where I don't know what the objective function is. There's like a little bit of notation. So x1 through xn, these are the inputs which we've done A/B tests, and we've observed this quantity for all of those x's. What I want to do, I want to think about choosing more x's so as to make this quantity large. So this is the utility that the decision maker will be able to obtain by looking at all of the A/B tests that we've run, picking her favorite, and then this is random because we don't know what u is. So I take the expected value. So our goal is to make this as large as possible. I'm going to do that via a one-step analysis. So imagine that I've run n A/B tests, okay? So if I weren't to do any more A/B tests, then the value that the decision maker would get would be this quantity u star of n, right? They would look at all of the panels of metrics. They would kind of introspect implicitly calculate their utility for all of them, pick the one for which this is maximal, and then like this quantifies in our model how happy they are. We don't know what U is, but that's going to be okay. Now imagine we get to do one more experiment at a point of our choosing, x, n plus 1. Well, if we did that and then showed the new set of results to the decision maker, this is the value that they would get by a symmetric argument. Okay, and you can write this in a way that's similar to the classical expected improvement, where it's the maximum of the decision maker's utility before I ran that experiment and the utility of the new panel of metrics. So this gives us an acquisition function, which we call expected improvement with utility uncertainty, where you just take the expectation of this difference in maximal utility values before and after an evaluation of y at x. And you can rewrite this in a way that hopefully makes it a little easier to see how you might compute it. So it's just the expectation of the positive part of the difference of the utility of the new panel of metrics minus the old best utility function value. And the way that you compute this, like in practice, is through sample average approximation. So what we do is we sample a collection of random utility functions from the posterior, given all the user queries that we've already done. And because they're modeled as being draws from Gaussian processes, we can deal with them using normal random variables. And then we also, so we have a proposed location X at which we're thinking about running an A/B test. We can calculate the posterior mean on the on y of x. So this is a vector because it's a panel of metrics. And then we have a Cholesky decomposition of the covariance matrix of all of those metrics. And then this is just a standard normal random variable, right? So this is a sample from the posterior distribution on the panel of metrics that I'm likely to see if I run an experiment with input x, and then I can push this through like my sampled utility function and subtract from it that same utility, the maximum of that same utility function evaluated at all of my historical data points. And if this is positive, if this is strictly larger than this, then we've gotten an improvement and we're happy. And if it's negative, then I set it to 0 with this positive part operator. So this is a quantity that if mu and c are smooth, then except for this, positive part operator, and except for the max that's implicit in this, then then this is a piecewise smooth function, and we can and this software package produced by Meta can optimize it, holding fixed these samples and holding fixed the samples from the posterior distribution on U in order to find the X that maximizes this quantity. Okay, so that's how this algorithm chooses the A/B test to run. Here's some illustrative numerical experiments. I think what's more interesting is like how we are deploying this procedure in real life to solve problems at Meta. But like one way that we evaluate it is we simulate decision makers who have utility functions where we don't tell the algorithm what the utility functions are, and then we simulate the process of using this acquisition function to run A/B tests, produce panels of metrics, and then we can see based on the held out utility function, how good the maximum utility across all previous samples is from a variety of different methods. And so here, this is the method I'm proposing. This is a slight tweak on it. And then here are some other methods that are kind of random, just random search. This is another method that's kind of inspired by the same kind of thinking using another acquisition function in Bayesian optimization. This is a classical multi-objective optimization. So that's how we choose experiments. How do we choose decision maker questions? So we're also going to fall back on the idea of looking ahead by one step, except our goal is different. So our goal is to understand which solutions Y have a high user utility U. And the approach is going to be, again, we fit a posterior distribution over the utility function using past decision maker responses to our questions. Our questions are, again, like, do you prefer panel metrics 1 or panel metrics 2? And then we're going to have an acquisition function along the lines of questions that were asked previously. I'm going to have an acquisition function over DM questions, over Y prime pairs. How do I construct this acquisition function? So let's, again, do a similar kind of thought experiment. So suppose that we needed to choose a solution to maximize the decision maker's expected utility based on the interactions that we've had with the decision maker in the past. And let's say, for the sake of argument in this thought experiment, that I know the feasible region for Y. All right, so I know if I vary X over the feasible space, what set of Y of X values are produced. Well, the thing that we would do is we would just choose the feasible Y that maximizes the expectation of the user's utility. Fairly simple. Let's call that U star of M, where M is the number of user queries we've made in the past. What if I get another question? Right, so I'm going to be offered the opportunity to show the decision maker 2 more solutions, Y1, Y2. And let's let R be the one that they choose. And let's assume that this choice is made according to the assumptions of the model. So they calculate their hidden utility on this one, hidden utility on this one. They take the difference and flip a biased coin, whose probability of saying 1 is large when the utility of this is a lot larger than the utility of this. Well, so if we had that extra question, and then we needed to choose a solution to maximize the decision maker's expected utility, we'd repeat what we did before, but we just have more information. So we would condition on the question we asked and the response. Let's call that U star M plus 1 because it has 1 more user query in it.
So Peter.
Yeah.
So it's two perhaps related questions. So this is, if the goal is to eventually find some input configuration that maximizes the preference.
Yeah.
Is it always the best strategy to learn the second mapping, learns the optimal region in the second mapping? Is that always the best strategy? Don't you want to be learning uniformly well? And kind of related to that is, is there a risk that if you try to just pick solutions in discussion, you may be picking YIs that are maybe not going to be generated by the XIs.
Yeah.
So.
So yeah, like I'm pulling the wool over your eyes a little bit by framing the preference exploration strategy in terms of this goal, right? So I'm saying the goal is to understand which solutions Y have a high user utility. A more nuanced and maybe what I should have written here is like understand which which potentially feasible solutions Y have high user utility. So it's like, so in the thought experiment that I'm, the kind of the warm-up thought experiment, I'm pretending that we already know the feasible region, but in reality, we don't know the feasible region. So like what you're really trying to do in this preference exploration step is you're trying to figure out, like, to support the A/B tests that you're doing are like, they're kind of expanding out the Pareto frontier. They're like finding parts of the Pareto frontier. And in the preference exploration step, you're trying to figure out, like, which parts of the Pareto frontier, if they're feasible, would be attractive. So the way that we're going to do it is we're gonna say, hey, if I knew the feasible region, what questions would I ask in order to figure out the parts of that feasible region that you like the most? And then that's going to work well for our real goal, which is kind of like to figure out which places that might be feasible we should focus our sampling effort. Does that help?
So it seems like you are doing like the first stage first and the second, so that gives you a better understanding of how to carry out the second stage so that it might be somehow. Is that
we are doing it iteratively?
Oh, okay.
Right. So we do preference exploration, then A/B testing, then preference exploration, then A/B testing. Yeah.
Okay. All right.
Yeah. Good. Okay. So if my answer to Kirthy's question didn't make sense, our goal here in preference exploration is I have a feasible set of Y values, and my goal is to figure out which points in that feasible set have a high utility for the user. What I've done is calculated this value, which is the value that the decision maker would get if I were to select a solution for them from my feasible set without asking any more questions. And then this is the value they get if I get to ask one more question. So the question that I want to ask in this thought experiment is the one that maximizes the expected value of this improvement, right? So this is the value they get before I ask the question. This is the expected value they get after I ask the question. And this value is the improvement. So like a one-step optimal acquisition function is one that maximizes V. Unfortunately, V is hard to maximize because it's got like some complicated nested like expectation, maximization expectation. But there's a simpler approach that does something equivalent, which we call the expected utility of the best option, which is another acquisition function. So it's just defined to be given two feasible points, Y1 and Y2. I calculate the maximum of the utility of those two options, and I take the expected value. And it turns out that if the decision maker gives me noise-free responses and some other regularity conditions are satisfied, then the query that's optimal for this simpler acquisition function is also optimal for the kind of gold standard acquisition. And there are some error bounds that we prove for settings when there are noisy evaluations. Okay, so and then there's one other challenge, which is that we don't actually know what the feasible region is, but we sample from the posterior over the feasible region, and it produces an algorithm that maybe is, unless you've worked in this area, maybe not immediately clear, but is fairly easy to implement in code and has similarities to the sample average approximation strategy. Okay, what I want to do is just show you a little bit about how this was deployed in some different domains. So one place is this was deployed at Meta for helping product managers to tune parameters in their products. Here's a screenshot of the user interface that was used to show different solutions to product managers where, they have like 5 different metrics. These would have real metric names. They're hidden, just for business reasons. And then the decision maker would say which one they prefer. Okay. And then, hold on just a second. The second way that this was deployed is for a product in Instagram where a generative AI pipeline was used to do automatic video dubbing of Instagram Reels from Spanish to English. So it's fairly easy to do the audio translation from one language to another. But what this pipeline does is it also processes the video to take the lips. You'll see in the video, the creator is speaking in Spanish. So then there's some video processing that changes her lips so that it looks like she's speaking English. So Mark is going to present this here. Oops.
Is we are experimenting with automatic video dubbing on Reels, starting with English and Spanish. So this is going to be a way that you can see more of the content that's out there, no matter what language you speak. And as a creator, this is going to let you reach a lot more people around the world, no matter what language you speak. So now you're going to be able to take your content and it's going to be in your authentic voice, speaking other languages if you want. And we're also doing automatic lip syncing. So it actually looks like you were speaking the other language. So let's check this one out.
De coco, banana y dulce de leche. Esta receta fue una de las primeras que subí a las redes. Hace poquito la volví a descubrir y le hice un par de modificaciones para que sea aún más deliciosa. With coconut, banana, and dulce de leche. This recipe was one of the first ones I uploaded to social media. A little while ago, I rediscovered it and made a couple of modifications to make it even more delicious.
Great. Yeah, so we have a couple of different applications of this, including tuning hyperparameters in vibe coding interfaces, where again, the direction that we're going is, and actually I am not on this paper, so this is from my collaborators, but where they take text from users, the text describes your experience using the vibe coding system. That then goes into an LLM, and the LLM produces pairwise comparisons that allow you to learn the utility function. So there's really like a lot of power that is being opened up through the ability to kind of work with text now in the same way that, historically computers have worked with ones and zeros. Now we can work with text in the same format. Okay, so I really appreciate all the questions, and I think I'll just conclude there in the interest of time. So yeah, we propose a novel framework for multi-objective optimization with expensive forward models. And the key idea is to model the decision maker as having a utility function, but we don't know what it is, and we have a Bayesian posterior distribution. We propose some novel strategies for some specific problems in this space. We also do some work with forward models that are MILPs that I didn't get a chance to talk about. But there's really, I think, a lot of interesting work to be done in this space, and happy to talk with any of you about, interests that you have in this direction. So thanks very much. I really appreciate everything.
We can take 1 or 2 questions, given that we're almost.
Hi, thanks for the very nice talk. So the building block of technology, or the method is the Gaussian processes.
Yeah.
And then, I don't work with them directly, but from what I understand, there's an assumption that any sample of data that's going to come will be jointly Gaussian, any finite number.
That's right.
Gaussian.
Yeah.
How much